We're going to get started in just a moment. Thank you everyone for coming. It's a real pleasure to be able to put on an event like this. We're so happy you could join us. We were positively thrilled at the level of attendance and that we've gotten. So we're really, really happy to see that. We're planning on doing this again every year. Given the format of this is essentially a webinar, more or less, a series of webinars. And so given the format, it's sometimes a little tricky to get the ideal interaction. So if you have questions or comments, there's a Q&A tab. It should be towards the bottom of your screen. Whatever comes to mind, if you have a question, just type it in there. We'll hold off on answering questions until the end of the presentation, but we'll get to them. We promise. So if something comes up you'd like to ask, just do so at the Q&A button. Today we have 3 sessions planned, 1 hour each. So after this, there will be 2 more. We hope you can continue to join us. And with that, we'll go ahead and get started here. I'd like to introduce Phil Goldblatt. He's been employed at Dairyland Laboratories in Arcadia, Wisconsin since 2014 and has been the NIR manager since 2017. He is responsible for calibration development and maintenance on Benchtop NIR instruments and also administers Dairyland's network of affiliated laboratories. He has experience with calibration development on several portable NIR instrument platforms and has served on the board of the NIRS Forage and Feed Testing Consortium since 2019. He graduated from the University of Minnesota in 2012 with a bachelor's degree in chemistry. Phil is currently pursuing a master's degree at Iowa State University in seed technology and business. Thank you so much for being here, Phil. Thank you so much for this very innovative presentation. I will turn it over to you.
All right. Can everybody hear me okay? Hopefully. So thank you to Blue Sun for inviting me to speak today. I really appreciate the opportunity. Let's talk about some interesting things in NIR, and I'm hoping people find my topic informative as well. So today I'm going to share results of a few studies we've done at Dairyland regarding performance of on-farm or in-field NIR instruments. So when I thought about giving the talk for this virtual conference, the topic is innovation in NIR for forages. So when I think about this, there are 2 directions that we're going in the industry. One is we're pursuing calibrations for new analytes. So here I've listed stuff like fiber or starch digestibilities, amino acids, fatty acids. We could add things like fermentation acids to this category too. Commercial labs, we're going to continue to respond to industry stakeholder demands and add new constituents as time goes on. I didn't really think that was as interesting of a topic for today, though. So the other vector for innovation in NIR for forages is the hardware that we're actually using to do the analysis. So if you've been involved in NIR for forages for a long time, you might have started out on one of these instruments here. This is your probably a 25-plus-year-old FOSS instrument. Some of us are still using them. They're very fine instruments, but a lot of us have moved on to newer and better benchtop instruments like this Blue Sun instrument here, which has the auto sampler and integrated RFID technology for improved efficiency, making less mistakes. There's also options like the DS2500 for FOSS that has improved resolution and a wider wavelength range. But we also have now these portable or on-farm NIR instruments. And as technology gets better, these are becoming a lot more affordable and a lot more accessible. So now there are a lot of platforms on the market and a variety of claims are made about them. So we're fielding a lot of inquiries from customers, and we feel it's necessary to become involved with the tools our customers use. So before we get too deep into that, I want to think about why we test forages. So some of us are making a ration to optimize animal performance. We're maybe timing harvest, pricing hay, doing plant breeding. These are all reasons why we might be testing forages. But to me, this can be generalized as we're trying to quantify variation in a forage so that we may make some kind of decision, whether that's buy or sell, change a ration, advance a new variety in a breeding program. So what we need to think about is NIR can always give you a number. You collect a spectrum, the math is what it is, and a number will come out. But it's important that we evaluate the accuracy and precision of that number before we make a recommendation to our customers on the use of any instrument platform. So what we did to examine the quality of on-farm NIR, and what we're going to cover in the talk today is how well can we measure moisture with these on-farm instruments. So telling what moisture is on the farm, even if you're not knowing anything else, that's going to help you out a lot. We're also going to examine how accurately we can measure some other nutrients related to forage quality, like NDF, starch, or crude protein. And we used in this talk, we're going to be covering mostly with the Neospectra from Silage, and how that accuracy compares to sending a sample into the lab where it's dried and ground and scanned in the conventional way. And we're going to examine whether we can use the portability and convenience of on-farm NIR instruments to improve accuracy by taking multiple samples. So quick disclaimer here for practical purposes, unless otherwise specified, the predictions that we're going to be showing are made from commercially available models at the time of scanning. There are some cases where that's not what we did, but I'll mention that explicitly. The other thing to note is that this data is, we can think of it as the best case scenario for these portable NIR instruments. So all of the scanning in this talk is going to take place within the laboratory setting on samples that customers have sent us, and we're only using a few instruments. We're controlling a lot of sources of error when we're doing these studies. So one, the environment is controlled. We're inside, the temperature is relatively constant, the humidity relatively constant. There's also no opportunity for sample degradation during shipping. We're loading the sample into the instrument and then weighing it up and taking it on through the drying process. So the portion that's getting tested on the portable is the portion that we're analyzing in the lab. The instruments used for scanning are also almost always represented in the models. So instrument to instrument variability is more controlled than it would be in the field, where if you got an instrument directly from the factory, it might not have representation in the models, and that can make a difference sometimes. But in this case, we're controlling for that. And then again, I want to emphasize that the exact portion of sample that's scanned in the portable instrument is carried forward for the reference analysis. So that's going to control a lot of our error. So the first thing that I'd like to show is performance on as is corn silage and fresh hay samples coming into our lab. And then just for clarity, we're also using a DS2500 here for the large cup, and we made a prediction model in-house that's not commercially available just for the purposes of this study. So for the harvest lab, that's partnering with John Deere, we did a validation set here, and we have a standard error of about 1.5%. We also did some studies with the SIO cup. And again, these are the commercially available models. And as you can see, the error is about the same, around 1.5%. So here we have the Neospectra from Silage. And again, I would say on a set this size, the difference between 1.5 and 1.68 is not very much. Performance is comparable. And here's this is a smaller set, but this is performance of the in-house model that we built on the large cup with DS2500 on corn silage. And again, we're in that 1.5 to 1.7 range for standard error. So for moisture on corn silage, we're all in the same ballpark of error with the 4 instruments that we looked at. We also examined moisture on green chop hay. So the standard error is a little higher on these. For the Silage, it's about 2.3%. And for the SIO cup, it's a little bit lower, but in the same ballpark. So with the green chop hay, that includes fresh samples that have been run through a forage harvester, but it also includes things like scissor cut alfalfa that can be a little bit trickier because they're very high in moisture, but also the samples are a little bit difficult to pack in the cup. So under laboratory conditions, depending on feed type, we can expect a standard error of about 1.5 to 2.25% on moisture or dry matter predictions on portable instruments. In my opinion, I think that's good enough to manage moisture. You can use it also to help you time harvest. I think it's a valuable tool there. So the next thing that we investigated was comparing the portable instrument and benchtop NIR, which would be the equivalent to the process of sending a sample to the lab, with the portable NeoSpectra platform from Silage. So we're going to go over some results on corn silage, starch, and NDF, and then we have some predictions on crude protein and NDF as well. Just so we're clear, we're going to be comparing the NeoSpectra predictions with the overall performance of the benchtop NIR. So for the benchtop, we're going to be using a large set of validation samples that are not the same. It becomes a little bit messy, in my opinion, because some samples in the NeoSpectra calibrations are not in the benchtop calibrations, and it makes it difficult to compare on a fair validation set. So for starch on the NeoSpectra, we're getting standard error of about 4% on corn silage. And when we take a large volume of lab results on customer samples on the benchtop NIR, we have a standard error of about 1.8%. That's the lab versus NIR on the benchtop. So we're looking at about 2.27 times the error of the benchtop NIR with the NeoSpectra platform. Now, if we look at NDF, we have a standard error of about 3.7. On the benchtop NIR, and again, this is a very large set, so I think this is what the error is going to look like if you look like at a very large volume of samples. We're at about 1.5% for standard error on the benchtop NIR. And again, 2.37 times the benchtop. So let's go to a different sample type. We're looking at dry hay. And for dry hay, this is anything that's less than 15% moisture. So that could be alfalfa hay, grass hay, small grain hay, anything like that. For the NDF, if you'll see that the R squared is a little bit higher here, but we're looking at about 4% for our standard error. And on the benchtop on this set, we're looking at 1.9. So now we're looking at 2.11 times the benchtop. So hopefully you're noticing a consistent theme that we're a little more than 2% higher, or 2 times higher error on the portable platform versus the benchtop. Next, we'll move on to the crude protein on dry hay. We've got 1.39% for standard error on the NeoSpectra for crude protein. Over the range of reference values, I'd say that you can definitely learn something from that. But with the benchtop here, we're at 0.6%. Again, 2.32 times the benchtop. So no matter what we're looking at for nutrient and sample type combination on the forages, we're looking at that same 2 to 2.5% range for the benchtop times that factor to get to the portable. So why should we expect these results? One, the benchtop NIR models are more mature. So here's a nice little screenshot from the oldest calibration for corn silage that I can find. This is from 2002, and we already have 590 samples in the starch calibration already. So I talked to Dave Taysom, and apparently we've been doing starch from the since the mid-90s. So we've been working on this calibration for a lot longer. Is it really fair to compare to something that we've only been doing for a couple of years? But I think the biggest factor here is the sample presentation. So for the benchtop, we're drying and grinding, and the portable, we're just scanning as is. So for the benchtop, we have, we got a picture of a sample in a ring cup. It's homogenized very well. The particle size is uniform and it's dry. Here is the same sample on the bottom right. It's very heterogeneous. The particle size is quite variable, and we have higher moisture content. So the title of this section was comparing portable and benchtop, but that's not actually correct, right? What we actually did was compare the portable NIR on as-is samples to the benchtop on dried and ground samples. And when we did this, the portable or as-is scanning had 2 to 2.5 times the error of the benchtop dried and ground scanning. Why might this be? So we touched on this a little bit in the panel yesterday. But moisture has a very large effect on the NIR spectrum. So this is 4 scans of all the same sample. So the teal and green spectra are from a DS2500 and the Neospectra on the as-is sample. So we took the same sample and scanned it on the DS2500, moved it to the Neospectra, then we dried and ground it and scanned on both instruments again. So the teal and green spectra have a lot less spectral richness and spectral features than the purple or violet spectra. And like John and Mark were talking about in the panel yesterday, that moisture has a pretty large effect on the whole NIR spectrum. So there's a lot less spectral features that we can look at to make a prediction. So what we wanted to do to really make a fair evaluation of the instruments is design a study where we can take away all of these other factors and make a fair comparison on the same basis for both pairs of instruments. So in this next section, these are all in-house models for the purposes of the study, and they're not available commercially right now. So these results might be a little different, and the calibrations will have less samples, but these are not the commercial ones. So what we set out to do was make a fair instrument comparison, and we scanned the samples as is on the Scyware Neospectra instrument. We transferred that same undried, unground sample to the large cup for a FOSS DS2500. We dried and ground the sample, collecting weights along the way, and we scanned that powder with the Neospectra instrument. And then we also took that powder and scanned it on one of our benchtop instruments that we use here in Arcadia. And we made models for each sample presentation for each instrument platform and compared them on a common validation set. So in this case, we're going to be comparing the benchtop and the Neospectra on the same sample prep basis, on the same nutrients, on the same samples. So this is as fair of a comparison as we thought we could make. So with this set of samples, we made an NDF model for the benchtop NIR, and for this small validation set we did, we got a standard error of about 1.1%. With the Neospectra instrument on the dried and ground sample, we were able to almost match the performance of the benchtop NIR. So this result, I think, is consistent with some other literature that's been published. I think there's one notable example where Paulo Berzaghi and Jerry Cherney published an article where they did something similar with dried and ground samples on a variety of handheld instruments. So this is not surprising to us. Now, NDF on the as-is sample was significantly less accurate. So here with the DS2500, we're standard error around 3. And with the NeoSpectra, our standard error is around 4 on our validation set. So, the DS2500 model is a little bit better, but it's still a significant decline in quality of predictions when you compare to the dried and ground samples. Now for the starch on the dried and ground, on our validation set for the benchtop, we got a standard error of 2.2. With the NeoSpectra, we were actually able to get a standard error of around 1.6. Now, whether this would hold up over a larger set of samples, I don't know, but I think it's particularly illustrative that, when we have the dried and ground sample, we're making much better predictions. And when we move to the as-is sample for starch again, for the DS2500, we're at 3.6 for our RMSE versus 3.92 for the SciWare. So I'd say that they're relatively similar again in standard error. And there's a huge decline in quality as we move from the dried and ground to the as-is sample. So let's kind of reframe our perspective on this. So for the NeoSpectra, our predictions on NDF on the dried and ground sample are very good. And when we look at the predictions on the undried on ground, where there's a significant decline in quality. Now, in the last section, we talked about how the benchtop the portable instrument had about 2 to 2.5 times the error as the lab NIR. Here, we see that the dried and ground sample error times 3 is equal to the undried on ground sample for NDF. For starch, we see the same thing. Good predictions with the dried and ground with the same instrument on the as-is sample. We're almost up to 4% on RMSE. So it's 2.5 times the dried and ground error. So that 2.5 factor keeps showing up here with the same instrument. So is it really the instrument that is causing the increased error? I don't think so. I think it's the presentation. So here's the benchtop, same thing. We go from very accurate NDF predictions up through the undried on ground, where we're having a 2.5% increase in error. Again, for starch, we're seeing error increase from 2.2% to 3.6%. And this is a little bit less of an increase in error. But again, when we go from the dried and ground to the undried on ground, the error increases significantly, even when we're using the DS2500, which I think we can agree is a quality instrument. So for those of you who are more accustomed to looking at calibration statistics, here's a chart of some relevant statistics here. And we can see that our standard error of cross-validation on the calibrations is about 2.5 times the dried and ground when you're looking at the as-is models, whether that's NDF or starch, and whether it's the benchtop or the SciWare platform. So to me, I think it's clear that the instrument isn't the problem, it's the presentation. And then here's another summary of our validation statistics. If you want a copy of this presentation, we can send that out to you. But again, if you look at it presented in this way, we're getting about 2.5 times the error on the validation sets when we move from dry and ground to as is. So one big question that I hear brought up all the time is like, okay, the error is higher on these as is scans, but can we overcome by averaging? We could possibly get something more accurate with multiple average samples than just one sample sent to the lab. So what we're asking is, can we take duplicate or multiple samples on the farm and average them to get a lot average that's closer to the error of scanning dried and ground on the benchtop? the more pressing question to me is whether portable NIR error is random or systematic. So if the error is random, and a lot of that error is relative to packing error, sampling error, maybe you're high by 4% on one starch measurement and low by 4% on the next one, high by 2, and so on. And you can average that out and get what would be a correct answer. Or is there a systematic error associated with the as-is scanning? So to test this, we designed a study where we would collect duplicate hay samples from lots of hay that were up for auction. We scanned each portion separately on a Neospectra instrument, and we compared predicted NDF values on each scan to the reference chemistry and to a lot average. So when we look at all of the data in total for the validation set, we have a standard error of 3.3, which I'd say is roughly consistent with the validation that I showed earlier. But when we look at the error on each sample from the same lot of hay, we see that that NDF error is correlated. So if we see this sample here, on both reps of that sample, we are off by 6% high. So averaging those 2 reps is not going to help the producer arrive at the right answer. So again, this is our total set of data. When we average the scans and compare to the lot average, which we defined as the average of the 2 chemistry reps, we do get some improvement in performance, but I would argue it's not significant. So on this set of samples, I don't think that we can say that averaging is helping us arrive at the correct answer. So, I would say that, the error was systematic, but it might not be associated with anything some inherent properties of the sample. Maybe that sample that was off by 6% twice was a species of grass that we don't have represented well in the calibration or something like that. We don't know. So can we find other instances of systematic error in predictions that would make us question whether averaging samples from the same lot will be helpful? So I think we can all agree that as we move from early growth stages of corn up through harvest, we are decreasing moisture and increasing starch. So moisture and starch are correlated, not perfectly, but they're pretty well correlated. And in the calibration set, starch equals, there's a regression from moisture to starch that has this equation. So if we go back to our plots of the same sample, on the undried, unground sample, we have this very prominent moisture peak and less spectral features that we can use to make predictions. So moisture has that huge effect across the NIR spectrum, and it's pretty well correlated with our analyte of interest. So what if all the NIR was measuring to get to a starch prediction was just the moisture? Well, what would the performance look like in this case? So if we made a plot with observed error on the Y, that's all this is here, the reference minus the predicted. And on the x-axis, we have the reference starch minus this regression equation here. And that's the difference between the true value and the regression to starch from moisture using the equation that I showed on the last slide. So if we made this plot and the error is systematic in this way, we would expect there to be some correlation here. So this is a different set of corn silage starch predictions than we showed earlier with the Neospectra. So standard error is 4, which I'd say is roughly comparable to what we showed in the previous slides. We've got a nice slope here close to 1. The R squared isn't that high, but it's there's certainly correlation there, and the bias is low. So I would look at this and say that while the R squared isn't the highest, I don't see any systematic error there. However, when we make that plot that I introduced on the last slide, we see that there is correlation between the error we'd see and the difference between the true value of starch and the value of this regression. So I think there's an argument to be made here that says, well, that difference could be just due to a poor lab result, error in the chemistry method, and the predicted value is really close to the right value if you would look at all of the samples. So I'm not sure that's an argument that can be made. Here we got some pictures of corn silage on the right that's failed due to drought, and then on the left we have corn silage that hasn't started making it near yet and putting on starch. So these are all low starch samples where the true starch value is very far from the regression equation. So on these values, that equation predicts that the NIR predictions would be very wrong in a systematic way, and that's exactly what we see. So I think we have evidence here that that error is systematic. If we scanned the drought corn silage samples and we scanned 100 reps of them, we would never get to a predicted value that was close to 0. So I think it's certainly a tool that can be used, but we need to take care that we're scanning typical samples when we're using the portable instrument. One thing that I also found very interesting is that we saw, and again, this is with the DS2500 calibration that we made in-house, and this is the same validation set that we saw earlier. We saw that the error is similarly correlated. So for the calibration that we made here, the R squared is again very high. So the error is correlated to the difference between the true starch value and the regression value very high. And I think this is a really important thing to take note of, because the systematic error is similar with a different instrument that I think is very high quality. And the model has been made using different software by a different user. And I think the important takeaway here is that there's nothing wrong with the portable instrument. There's nothing wrong with the user of the portable instrument or the people who are making the model. It's just an inherent difficulty of scanning the undried, unground samples. So just to summarize my takeaways from the studies, I think we can say that on-farm NIR moisture or dry matter error is about 1.5 to 2.25%. If you're comparing the on-farm NIR instrument error to what you would get in the laboratory on non-moisture nutrients, you can expect about 2 to 2.5 times the error of the benchtop NIR. However, if you take an on-farm instrument like the Neospectra and scan dried and ground samples, you can get comparable performance to a benchtop instrument. So the elevated error that we all have seen on a variety of these on-farm NIR instruments is likely due to sample presentation, namely not drying and grinding the sample, not due to the hardware or the skill of the user making the model, the skill of the person actually scanning the sample. It's an inherent error of the sample presentation. We're drying and grinding samples in the lab for a reason. So, and again, the portable NIR instruments are most effective when the sample being analyzed is relatively dry and uniform in particle size. And with forages, if we're not drying and grinding them, they are not. So before we wrap things up, I just want to say special thanks to my team here. That's Nick, Nicole, Joe, Holly, and Val. I'm not a one-man shop here, so I really want to thank everybody else for all their hard work that's enabled us to go through and do all these studies. And thank you for your attention, and I'm glad to take any questions you might have.
Josh, I think we
Yeah,
lost your sound.
I can't hear you either.
Sorry about that.
Okay.
Thanks, Phil. Very interesting presentation. Very, very interesting points. A little bit to digest, but does anyone have any questions? We've had some comments. Thank you. A great presentation. Anyone have any questions maybe about the instruments or the process? We'll give everyone just a minute just to let them put their thoughts together. Very interesting conclusions. I wasn't anticipating it working out exactly the way it did. Well, if you have any questions that come up later, come to mind later, you can direct them to us. We can share them with Phil. Oh, here we go. Okay. Is there research forthcoming for the handheld instruments that would include digestibilities?
I will say yes. I think it's gonna be a tough hill to climb on the undried, unground sample. Based on what I see here, if you're willing to dry and grind a sample, you can probably buy one of these portable instruments and get very good predictions with one of those. But if you're not drying and grinding, I think it's just a tough hill to climb. Where we think that there's a lot of potential for instruments like this is feed mills. Like in the feed mill, you're working with something that's not dried and ground, but pretty close, right? Like if you have a dry distiller's grain, no one's dried it and no one's ground it, but it's basically dried and ground. Soybean meal, there's not a lot of moisture in that, and the particle size is relatively small and uniform. Canola meal, something like that. So I think that there's a lot of potential on instruments like these for the feed mill. I think forages is going to be tough.
Thank you. A couple more questions. Would drying the sample first, but not grinding it, give you the same error?
I would think that if you dried corn silage, and didn't grind it, and you built a model based on that presentation, you might get some increased accuracy. I think corn silage is the most difficult sample type that we have, because we have, the kernels that are almost all starch and no fiber, and then we have stalk and leaf where there's no starch and lots of fiber, and it's very difficult to get a representative scan of all that material. So like what we do with the NeoSpectra instrument, we have like a big cup. It's about this size. And then on this, it'll spin around in a circle. But, I think it's very difficult if you have a non-homogeneous sample to get accurate results. And as we talked about yesterday in the panel, and then in, I think, Rocky's talk as well, if you have different particle sizes, that is going to affect the NIR spectrum. So without drying and grinding, you are probably going to see increased error.
Thank you. And one more question. What can you say about the polyspec and agra NIR? Do you have any?
I think we did something with the polyspec a long time ago that was before my time. I personally can't say anything about either of those. I think that you're going to run into the same problems. But again, I don't want to draw any conclusions about something I haven't personally worked with. So.
Okay, thank you. That I think concludes the talk. I don't see any other questions. We're about 11:40 Eastern time right now. Our next session starts in 20 minutes at the top of the hour, so everyone has time for a break before our next session starts. Phil, thank you again. Very, very detailed, very, very methodical. We really appreciate you sharing your findings here today.
Thanks. If anyone has any questions, feel free to shoot me an email. Thank you.
All right, thanks. Thanks, everyone.